Today we're going to talk about our implementation of diffraction multifocusing stacking, which uses the watershed transform to help resolve diffractions. Diffraction multifocusing was developed by Alex Berkovich. The relevant reference is this one from geophysics. The general theory is mathematically complicated, but the special case of multifocusing stacking can be expressed as a modification of normal move-out correction, which is the approach that I'll use here. Normal move-out correction uses common midpoint gathers to facilitate interpretation of every observed event as being a reflection off of a flat layer for which the bounce point lies directly below the bin center. To target diffractions instead, we drop the common midpoint restriction and instead include all traces whose shot and receiver both lie close to the bin center. This leads to very large folds, but you need that to enhance small diffraction amplitudes and to knock down the reflections destructively. We also have to drop the assumption that the target lies straight below the bin center. Diffractors will have lateral displacements, so we're going to have to search for them using zero offset ray paths that tilt away from the vertical. To give consistent coverage of the lower half space, we choose a set of search paths whose tilt and azimuth angles form a geodesic grid. The tilt and azimuth parameters add 2 extra dimensions to the usual line, bin, and time dimensions of the conventional stack, so it's fairly evident that manual picking of diffractions isn't going to be feasible, not from a 5D stack. We'll need to automate the process by using semblance to pick out the positions of the diffractors. I put this viewer together to show what these 5-dimensional semblance volumes look like. Let's start with what's familiar. The middle plot is a semblance trace and the right plot is a semblance time horizon. The X shows where they intersect one another. So these are 2 perpendicular slices through the usual line, bin, time space of conventional stacking. But since this data is 5-dimensional, whatever's shown in the middle and right plots has to correspond to a particular tilt azimuth direction, and its position is shown by the X in the left plot. The left plot, for its part, shows semblance in all possible directions for the time of the X in the middle plot and the line bin position of the X in the right plot. All 3 plots are mutually perpendicular. Navigating through tilt azimuth space, and all 5 dimensions really, you can see how the features change. What we hope is that each major semblance maximum corresponds to a real diffraction, but how are we going to use that information to pick out diffractions from the 5D stack? We'll use the watershed transform, which is an image processing technique that is designed to cluster together pixels that are all associated with the same local maximum. This is the watershed transform of the semblance data that I just showed you. Each colored region should correspond to a diffraction. Let's navigate around a little bit. Now at each bin, the tilt azimuth coordinates of the local semblance maximum within any particular region and the time extent of that region through its semblance peak should tell us where to find the signature of the associated diffraction in the 5D stack. Here we have some results for lines 101 to 105. These are certainly encouraging. Quite a few diffraction hyperbolas are visible. However, there are a couple of caveats. One of these is that many of the hyperbolas have an incomplete appearance. This is probably happening because of simplifications that we had to make to our watershed transform algorithm. I go into more detail about these in the talk. They were necessary because of computer memory limitations. What we ended up having to sacrifice was lateral continuity of events. The more serious problem, though, has to do with reflection energy. Reflection amplitudes interfere destructively during diffraction stacking, the same way that diffractions do in conventional stacking. But inevitably, some of the reflection amplitude still comes through, and they can overwhelm diffraction peaks on the semblance diagrams. So these results were obtained by running the input data through FK filtering to knock down the reflection amplitudes artificially. That only works because these layers are flat, and it wouldn't be good enough for production. I'll also show some time slices through that last result, starting around 400 milliseconds, where a number of events start to come in. As you move down, you can see that these open up into circles, just as you'd expect from diffraction hyperbolas. So the bottom line is, the technique is promising, but it's not yet ready for production. There are too many unresolved problems for that. Thanks to everyone who deserves it.